You're okay. It's red now. Okay, there we go. So what would we like to start with? I've got topics lined up for the day. We're going to look at electric motors, which is just applying the ideas of electromotive force, force on electrons moving in a wire. Yeah, and then the electric fields, magnetic fields from wires that are carrying current. And I do have the homework solutions loaded up from lesson 21 and 22 from yesterday. So what would you like to see? Anything you'd like to see to start off with?
Sorry, could you pull up number 1?
Like number 1 from
this
one? Yeah.
This one.
So this one had this like MHD propulsion boat that if you look in the textbook, it describes that it has electric plates, parallel plates inside of it. And if you have, it applies a voltage across the water, right? And so the water ionizes. I guess this maybe would work best in salt water, of course. So they end up with ions repelling from that negative plate. Let me use my pen here. Show in motion here. So if we had a negatively charged, picture is like just basically you have excess electrons, let's say. So that's going to repel across here, right? So now you're like, oh, okay, so I've got my left hand with my thumb pointing in the direction of electron flow. And then there's also inside the boat a large magnet, probably an electromagnet or whatever, but to be able to create a magnetic field. And so you've got an electron going this way, like really it's a molecule of water, right? But it has a negative charge, so it's repelling away from the negative plate. So you've got electron flow to the out of the page, sort of, or however we want to describe this in this picture of this boat, towards the left side of the boat, the port side of the boat, if you're a boater. Anyways, and the magnetic field is up, and so the palm is pushing backwards, and so the molecules of water actually end up with a push backwards. Okay. Review from grade 11 physics tells us that if there's a force of the boat on the water, then there's a reaction force of the water on the boat, and so the water being pushed backwards, of course, leads to a thrust force forwards. So they put voltage on these plates, and water shoots out the back, which is pretty cool. There's a video about that. I don't know if I'd be able to find it right now or not. I think it was Action Lab, water flowing voltage. Yeah. Jump stream of water. Send water through. I forgot about this video, and it just occurred to me. I don't know if this is the one or not. Let me just do a quick check. Ads. Remember I said, oh, here comes an ad from Grammarly. There we are. Is this the one? Is this the one? Oh, thanks. And sound.
In my last video, I posted
Don't
about
think this is the one.
Cable, and the signal.
There was just
alligator clips. If we're not connected to the internet.
No, it's definitely not the one. I'll have to see if I can find it, but he just basically had, parallel plates in water and Action Lab. If I come across it and it's good enough, I'll show it to you. I just thought maybe I'd find it on the fly here, but not so much apparently right now. Just stubbornly continuing, but no, it's not showing up. Not positive it was Action Lab, but it probably was. That's the one that I see all the time on the internet. Anyway, so more questions about online stuff? Or no, or on this homework stuff, I should say. Did that solve your question, first of all? both?
Yeah, I did. I was just a bit confused about how to visualize it, but that
Yeah,
helped.
for sure. Yeah, a little bit weird. So what else should we do? I think we got the first few were the first type of question where it's like just plug in the numbers, plug in the numbers, get the force that would be on the thing. I even put a picture of my hand in there to help you visualize the left hand or right hand rule. I guess that one was. We must have had flow of positives, right? Yeah, proton. Yeah, so that's my right hand, and so on. When we get into this circular motion question in number 4, it's all worked out there for you, but basically you figure out the magnetic force, the force of, the motor force, or whatever you want to call it on the charge. And then you say, well, that's causing circular motion. So boom, boom, boom. It's not too bad, really. It's just intimidating when you hear circular motion, but use the equation from the sheet. So any questions about that one, any of that stuff, or any of number 22 here? 22, I think these ones, if I remember right, they were all just like plug in the numbers to this new formula we know, and you're good to go. So it should be fine, right? You're just applying the equation, right? And so no one's asking about that stuff. That's maybe hopefully a good sign. The one thing it's still I'm lacking on in this online teaching experience is the idea of assessment. We've only done that one quiz. I haven't even actually, gone into mark those yet. It won't take me long once I do it, but I haven't. I need to look to see if they're there and make that happen. I'll do that this weekend. I was thinking about for a unit test for electromagnetism and we haven't had a lot of little quizzes, so I'm assuming it's a safe assumption that people are going to sort of rather have some small assessment items, at least anyways, maybe before having a test or maybe instead of having a large group test. So in other words, I'm thinking you would like it if I said, hey, we're going to have a small quiz assignment type thing on forces, on electric forces, and then one on, maybe on forces per charge too or something, and then one on energy, and then one on energy per charge, which is potential, right? So like one on force, one on field strength, one on energy, and one on potential, and that's kind of like, that summarizes a heck of a lot of the stuff so far. And then does that make sense?
Okay.
Yeah, I'd prefer a bunch of mini ones over like one big one, personally.
Yeah. I think it would just that's what we would normally do in class. So I think we should maybe try and continue that tradition of so it works to help people be successful. So I don't maybe what I don't know if I want to do it as like schedule a quiz for Tuesday and then schedule a quiz for Thursday, because my goodness, it'll take forever to get out to that. But maybe since these are more being done as kind of like assignments, I'm just going to start emailing them out, and when you get, basically we'll try and make it a reasonable amount of time to get them done, but rather than me waiting until, Thursday and next Tuesday and whatever, like to get these out of the way, I'll just start sending you small groups of questions. Does that make sense? And they're just mini assignments. Think of, basically it would be quizzes if we were in school, but you're doing them on your own. So
yeah, that makes sense.
okay.
When did you start like sending them out?
So I'll probably end up sending like the force one out today, and then like look at as you get them, you're going to look at them almost like as reviewing, right? For reviewing material, and you're just doing the questions and after doing all these assignments, if we were to have a unit test, it would be like, wow, yeah, I basically put all these questions together and you got yourself a unit test, like that's kind of what I'm thinking of. I'm just struggling a little bit myself with the concept of how assessment works in this situation. That's all. But yeah, at least get you doing some questions and handing them in and getting feedback on them and marks and so on, right? So get the ball rolling that way.
When you say assignments, like, would we use our notes, or like are they quizzes where do them like
I'd prefer
a quiz class?
I think I'd prefer in an ideal situation for them to be quizzes. but I know I can't really, it's not something I can really police for everybody in the course at this point. So I don't think it's really fair for one or two people, to be like full on using their notes and everybody knows it, and other people are being in high integrity and having someone supervise them and doing it as a quiz. Like there's inequity there, and I don't like that. It's been bothering me a little bit from even past courses when I've felt like I was trying to do it right, do it the right way, and so on. So I'm going to call these assignments. So you're just going to tackle the question. You can use your notes. You can use your equation sheets. Just basically get a nice, well-written solution for the questions. Okay.
Okay.
All right. Yeah. So let's move on then. So we're going to look at electric motors. A couple different examples of it in that. And actually, before I get going with that, I want to show you a neat video from my buddy here, Action Lab. Somewhere in all of these windows, permanent magnet that turns on and off. So his video is basically like, can you, is it possible to turn a permanent magnet on and off?
Hey everyone, today we're going to be seeing if it's possible to turn off or block a permanent magnetic field. So it would be nice if you got something stuck to a giant neodymium magnet like this one, that you could actually remove it if you could just turn off the magnet. Now, if it were an electromagnet, you could easily just turn off the current going through it and it would no longer produce a magnet.
So I didn't show this video at the time when we talked about magnetism because we hadn't talked about electromagnets yet. But what is he referring to in terms of when he's saying if it's an electromagnet? If this is a big coil of wire and you just had a big voltage going through it, you're going to create a north pole, using the hand rule for electrons going around in a circle, and you'd get a strong magnetic field there, and it would attract the nails. And then if you turn the electricity off, disconnect the voltage, they would let go of the nails, right? So that's what he's referring to there. So in our descriptions of electric magnetic fields from wires and so on, although have we done that one fully or not? Magnetic fields from wires. Maybe I'm still a little bit early. Yeah, I kind of am actually. Oh well, whatever. It still relates to mostly just to magnetism. So you're going to be seeing how we can make magnetic fields with electricity in the next lesson anyway. So here we go.
But with permanent magnets like this neodymium magnet here, it's not so easy to turn it off, but it actually can be done. So let me show you two ways that you can turn off a magnet or block its magnetic field. And then I'll show you the true way that you can actually turn a magnet off and on again.
I remember this being
So let's start off with a pretty decent sized cylindrical shaped neodymium magnet. This
what did that
magnet's
say
pretty,
there?
so let's start off with you can actually turn a
magnet. Try and block it with steel, trying to heat it up. Basically, that's what we've seen in the past about the domain theory business, right? Where you can just rearrange the directions that the individual atoms and groups of atoms, the domains of atoms, are pointing. If you rearrange that, it'll, so if you take that big, huge magnet he's got there, which probably is like a $200 magnet, so you're not going to do this, but put it in a furnace, like a blast furnace, and melt it, it's not going to be magnetic anymore. So he's going to look at trying to block it with steel, see if that works. He's going to talk about the idea of and I think he shows he melts like a little magnet and ruins it. And then he's looking at whether there's like an on-off switch where you can just turn magnets on and off. So that's what he's going through here.
On again. So let's start off with a pretty decent sized cylindrical shaped neodymium magnet. This magnet is pretty strong by itself. So let's see if we can just block it by putting some metal over it. Now we're going to be able to see the magnetic field by putting this special magnetic paper in front of it that lets us see the magnetic field. So first let's take this sheet of non-ferromagnetic metal here. So you can see the magnet does not stick to it. But you can see that the magnetic field easily penetrates this. So I wasn't able to block the magnetic field here. But let's try to use a piece of steel now.
So that explains why stainless steel isn't magnetic. So a lot of people have stainless steel fridges, and you can't put you can't stick magnets to the front of the fridge. But now they're that people are kind of annoyed by that. Some people are kind of annoyed by that. I'd like being able to put things on the fridge with a magnet. So now it's pretty common for you to be able to put a magnet on the front of a fridge. I was actually just at my parents a couple weeks ago. Don't tell anybody. And they have a new stainless steel fridge, and they're showing like it's actually magnetic. And I said, well, you know, like basically they have a sheet of ferromagnetic material like steel behind the stainless steel, so the magnet is able to bond to the iron based material that's behind the stainless steel. Stainless steel is a special alloy, right, that just isn't ferromagnetic anymore because of the way it's bonded. But the magnetic fields go through that stainless steel no problem to the ferromagnetic material behind it. So if you have a layer, my fridge here at the house doesn't have that. You can't put a magnet on the front of the fridge because it's just stainless steel. They didn't bother to put the layer of regular steel behind it. So that's just something that was pretty easy for people to do. I don't know why they didn't do it originally, knowing that people like to put things on the fridge with a magnet, like a good physics test mark or something, you know, put it on there with an A on it, you know, good old days. But anyways, so there's a sheet of steel all rusty.
But even with the piece of steel, it's not completely blocking the magnetic field.
So the next step is, you know, to see like, yeah, can you block it with steel? Well, not really, right? Because you can see the magnetic field still penetrating through the steel even.
Right behind here. Pretty cool. It looks like we have X-ray vision through this steel here. You can see the magnet behind it. But if we get a thicker piece of steel and stick our magnet to it,
it's a very strong magnet.
Now we can't see anything. So we didn't actually block the magnetic field here. What we actually did is create an easier path for the magnetic field lines to go through.
So that's critical, we think. We created an easier path for the magnetic field lines to go through. So without the steel, picture the magnetic field lines doing this, around and around, right? Like this. So the magnetic field would penetrate out quite far because it would be going through air and eventually back to the magnet, right? What happens when you put the big chunk of steel here is the magnetic field lines are like, you know what, I'm not bothering to try and go through the air. I'm just gonna travel in this steel here. And so it stops the magnetic field lines from going out so far as they normally would. And that's because, of course, the permeability, right? The magnetic permeability, the K value that they used for this thing, they've all Ks everywhere, of course, right? But like I was explaining or talking about yesterday, I was annoyed with. But yeah, so because it's like, what is it, 7,000 times easier for magnetic disturbances to go into steel than through, you know, go through steel than through air. They take advantage of that. They end up just doing their thing inside the steel instead of penetrating way out farther through the air.
The steel provides an easier path for the magnetic flux to go through than the air. So that's why it's able to block it. Although it's not really blocking it, it's just creating basically a short circuit path for the flux to go through. So it doesn't show up in the air on the outside of it. So when we try to stick anything to it, it doesn't stick.
So it kind of effectively blocked the magnetic field, but in a different way, right? So that big iron spike isn't attracting to the magnet, even though it would attract the magnet if it was only this far away from it without the steel there, right? So he did effectively end up blocking the magnetic field there. There we go.
Longer be able to contain any more magnetic flux, and so it'll just penetrate into the air again around it.
Oh, it says,
so let me
he
show
had
you
said
with
just
my
before that,
giant
if you had a strong enough magnet, you would actually penetrate that steel.
neodymium magnet. Oh.
Techniques you have to use with this kind of magnet, so you don't crush your fingers.
All right, so now I have my magnet stuck to the back here, even though it's through a few inches of acrylic, it's still on there very tight. But now you can obviously tell that some magnetic flux still goes through the steel.
Not as much as if he was putting that nail right to that block, he probably wouldn't even be able to take it off without two hands and using his left foot, to pry against it. But here it's like it's sticking quite convincingly to the steel, but not as strong as it would if it was directly to the magnet. So it's still kind of shielding a little bit.
Saturated and is letting the magnetic flux go through it and penetrate the air again.
So he didn't really say it, but along the edge here, you're going to see a line of the edge of the steel.
Saturated
right there. See how you can see the edge of that shape of that X weird shape of metal? So you can see that there is magnetic flux coming through the steel.
Letting the magnetic flux go through it and penetrate the air again. So the bigger the magnet, the more steel you need to block that magnetic field. Now, one way you could turn off the magnet but not turn it back on is by heating it up. For example, if I just stick a little neodymium magnet to this steel plate here, now if I heat this magnet past its Curie temperature,
So
which
there's a little
is the
magnet
point at which
stuck
the
there.
magnet loses its permanent magnetic properties.
And eventually heat it up enough and it
Oh,
falls to the ground because it's not magnetic anymore.
no longer sticks to it at all, or anything that's steel. So I basically destroyed this magnet here. So at around 600 Kelvin in these neodymium magnets, all of the magnetic moments that were initially pointed in the same direction got enough thermal motion that they weren't
Magnetic moments means like directions of each little domain.
all pointing the same direction anymore. They became so disordered that it's no longer a magnet. But the problem with turning a magnet off like this is you can only turn it off. You have to remagnetize it somehow to turn it back on. So when we
What would the somehow be? Expose it to a really big magnetic field. Get them all to line up again. Possibly have to, like, I don't know if you have to heat it up in the process or not. I'm not sure.
heat the magnet past its Curie temperature, we can turn it off. Or when we try to block it with thick steel, we can turn it off. But in both of these methods, we can't really turn it off and on. But what if there's a way to intelligently turn off and on permanent magnets? Well, it turns out there is a way to do this with something called a mag square.
So it's a mag square.
So notice on here,
I had never heard of this before. I like this guy's videos because they learn new things.
it has an on-off switch. This is a permanent magnet. This is not an electromagnet. So right now it's on, and it can easily pick up these steel pieces of metal here.
So no batteries, no electromagnets,
But then
nothing like
watch
that.
what happens when I turn it off. They just drop off like nothing. And it can't even come close to picking them up again.
So how the heck does that work? Am I right? Like, that's a permanent magnet, no batteries. It's same as one of those ones that he's, the big one or whatever. It's just got something, a permanent magnet in there. How does that work? Any guesses? It's weird. I wasn't sure either when I first saw it. So I'll just play it.
Non-magnetic now.
And then he turns it back on.
Here's a huge iron nail here. Turn it on. And I literally cannot pull this off. It is locked on there.
Pretty strong unit.
But luckily I could just turn it off. And it drops off like nothing. Then it's not attracted to it at all.
So
You can use it to
the key to figuring this out is to think of what the magnetic field lines want to do, right? They just want to go to another, like to an opposite field. So like the north wants to go to a south. And so he's going to show us eventually here that there's actually two magnets in there that are engineered inside here with this switch, and there's probably some gears or whatever, but it flips the direction of one of them. And if you end up with two magnets side by side, and you have a north and a two norths both pointing down, then it's super strong magnetic field. But then if you're able to change one of them, rotate one of them so that it's the opposite way, you've got a north and a south together, then the field lines are perfectly happy just jumping from north to south, right side to side. I'll show you that.
Metal.
He's going to show you soon here.
I have a tiny, there's so behind this paper here.
All right.
So how does this
There we go.
work? How is this turning a permanent magnet off and on again? Okay, so let me show you how this works here. I have a piece of steel behind this paper here. So you can see that I have two neodymium magnets here that individually stick to the steel. Now I've marked the north end of these magnets here so you can tell which side is pointed which way. Now I can put both of the south sides of the magnet on a steel coin here, and it will still stick to the steel plate behind it. But if I change the direction of one of these magnets, so that one of them is now north side facing up and the other one is south side facing up, notice that it doesn't stick anymore. So now if I were just to say that this steel coin were my magnet, you can see that it's not magnetic right now. But then if I just flip the direction of one of these magnets, then it becomes magnetic. So if you didn't know what was inside the black box here, you would say that I was turning this magnet off and on, when in reality, all I was doing is switching the direction of one of these permanent magnets inside of it. So why is this happening? Why is this so efficient in blocking the magnetic flux? Well, the reason is, remember that the magnetic field lines are always going to try to go from the North Pole to the South Pole or vice versa. So they're going to want to...
So in this one right now, they want to go around through whatever they can around to here, right? So if it's through air, then it's just through air. It's doing its thing. If there's metal here, though, that's easier to go through, then they end up interacting with that metal and going through it easier, and that's what's causing the magnetic attraction, right? Because these both want to go around and whatnot. If the the magnetic field is penetrating through this metal coin that's on there, right? If you flip these, now the north to south is going to be perfectly content to go through this metal here, and it's not going to have any use for any other metal nearby.
Yes, but if you put a piece of steel there, then the steel is going to want to give it a shortcut to go from the North Pole to the South Pole. So when I have them face the same direction, they're basically like the same piece of magnet here. So the magnetic flux lines are just going to go from this side around to this side.
So that whole piece of metal is acting like a south pole, right?
So when I put another piece of steel close to it, it's easily attracted to it. But then if I switch one of these around, now the magnetic field lines, they just want to go in a short little circle right there because it just wants to go from north to south or south to north. So they just want to form this little short.
So notice that coin, he could stick it to this side, right? But then nothing else would stick beyond that on either side because they'd have their short circuit on either side. I don't know if he shows that or not. I don't think so.
So they don't really want to escape from this steel plate here to go into this other one below it. So it's not really attracted to it at all. So the way you turn it off and on is just by manipulating the magnetic field. So they always want to take this shorter path, and they don't want to go through something outside of it. And that's actually exactly what's going on inside of here, except just to a more precise level. And so if you can get two of these on top of each other, and you could just rotate them 180 degrees, then you're basically doing the same thing I was doing by flipping one of these 180 degrees.
I guess the fields of these aren't like a north on one end and a south on the other. I guess they're like a north and a south side to side here. And so he's saying if you have two cylindrical magnets and you rotate it 180 degrees, I guess that's how it physically actually works inside of there. You'd have to just, it's the extra information about what the magnetic field shape is around those.
Cylinder, you can completely...
So if you took a compass and put it right here, the north might repel from here. And as you move the compass to the right here, the north would all of a sudden go woof and point into this side, right? So you picture the north repelling from here and then attracting to there based on what he's saying. And so if you rotate them, then you've got basically north and south all paired up and happy.
Steel on either side, and then you can completely block the magnetic field and make it directed so it goes from one side to the other. And thanks again for watching.
So something related to that, if I don't know if you wouldn't have ever, I doubt, have looked at fridge magnets. But a fridge magnet is like this big sheet, right? And it has some thickness to it. And in that fridge magnet, there's actually sort of, I'm forgetting how to draw it exactly. Basically, there's a bunch of columns of magnets, and it's like a north in this end, and then a south, and then a north, and then a south, and then a north, and then a south. And I think I've normally drawn it with like a point on one of the ends or whatever, but it doesn't matter. So north, south, north, south, north, south. And so then when the ferromagnetic material of the fridge, if it's magnetic, right, you put the fridge near it, then the reason the fridge magnet sticks is because the magnetic field lines, instead of them wanting to go, instead of them trying to go through the air and around from one to the other, instead they're like, ooh, sweet, a shortcut. Boom, I'm just going to go like crazy through this metal. And going like crazy through that metal, picture like 3 field lines penetrating through the air versus 3 field lines like taking a shortcut through the metal. That's what's causing the force of attraction. So if you take a fridge magnet and flip it over, so flip this thing over and look at the fridge magnet, like the black side of it, and you put iron filings all over it, and I usually put it like a piece of paper over it, but you end up with the iron filings all lining up in little lines like this. So if we ever end up back in room 124, remind me to show you fridge magnets, because they're kind of neat. So iron filings all like this, and what they're doing is they're just lining up between a north and a south, each along the way, north, south, north, south, north, south. Yeah. I think what else I was going to say about that? I thought there was something else, but maybe not. Anyway, so that's just a little bit about magnetism that we just add to what we had seen before. So here we go. This is more, this is like using the idea of the motor force, right? So picture what would happen in this situation here. We've got a horseshoe magnet and a wire that's sort of going like in and out of the page, if you will. I'm trying to, it's obvious I'm trying to communicate a three-dimensional look. And then if I just look from the front directly on, I've got the horseshoe magnet, I've got the cross-sectional butt end of the wire, and I show the electron flow going away from you, like into the page. Those are the tail feathers of an arrow going away from you. So what's going to happen in this diagram? So we can analyze based on the motor principle hand rules, and we can also analyze based on actual like magnetic fields. Okay, so I want to analyze both of those. So first, let's just do the kind of the easier one where we're like, point your thumb in the direction of electron flow with your left hand, right? Or the imaginary positive flow in the opposite direction with your right hand. But here I've got my thumb of my left hand pointing sort of towards the screen, and then I'm extending my fingers down from north to south. And in this situation, hopefully you're doing this with your hand as well, so you can help yourself visualize this. But your palm of your hand, you can't have your palm of your hand facing to the left. If you have your thumb pointing in electron flow and you have your fingers extended out downwards away from the north, right? You can't have your hand the other way. So your palm of your hand's naturally facing to the right. And so what we show here is that we have the magnetic force on the electrons is to the right. And remember, that's the force that is like QVB, right? QVB sine theta, right? The amount of charge going, the velocity of the charge, the magnetic field, and so on. And then we also converted that to ILV sine theta. Those are the equations that have to do with this, right? So either you're talking about the quantity of charge and the velocity they're going in the magnetic field, or you're talking about the current that's flowing, the length of the conductor that's in the region of the magnetic field. So I guess L would be sort of, in this region here, that'd be L, right? Yeah. So you can picture the quantitative version of this as well with equations and not working the numbers, but you can also talk about just qualitatively which way it would go using the hand rule. So the hand rule here would have looked kind of like, pardon my artistic skills here. Ooh, let's have a bad start. So got my hand sort of like this, and then my thumb was pointed like that, right? And so my thumb, I'm just looking at my hand here. I guess my thumbnail's kind of on the top, and I can't see my fingernails at all. This is the palm of my hand. And so it's pointing that way. That's the magnetic field or magnetic force. A little bit easier to draw, obviously, if it's just a two-dimensional thing, but it's going to be harder to draw the actual hand rule now. But thumb into the page, fingers north to south, and we're again going to have this magnetic force on the electrons. And so whether we're talking about force on the electrons itself or we're talking about force on a wire, this is the idea, right? So this one here is force on electrons itself. I'm going to say Q's actually maybe instead, right? Force on the charges directly. And this is the combined force on the wire. And so the idea is if the electrons have a force to the right on them and they're trapped in a wire, then obviously they're going to make that wire push to the right. Any questions about that part? So that is based on the hand rule idea. I want to show you as well the analysis that's that this hand rule is developed from, right? They were able to predict which way the force would go before the hand rule was thought up and made up to help people remember. And so how that works is based on, so I'm going to just maybe make a note here. Direction can be analyzed based on direction of magnetic force on charges moving in a magnetic field. Can be analyzed based on the original, based on, let's just go based on opposites attract. Fundamentals, right? That's what I kind of wanted to communicate there. Opposites attract, and of course, likes repel. So they can be, okay? It's just that the hand rules make it so much easier. I need to gain control of my screen here. There we go. All right, so we know they can, right, be analyzed. Well, I'm telling you, I'm going to show you that they can be. It's just that the hand rules are easier, right? But curious, right? We're just told, you know, that these hand rules make sense, and we do it, and we're like, we don't necessarily know why, what's going on. So this is more about why the hand rules are true. So this page is ready to go here. I'm just going to talk us through it. So the red is the direction of the magnetic field, down, curving around like that, right? And then the electrons flowing actually make their own magnetic field. And so electron, left-hand rule, you got the electrons going, you know, up into the page like that. And then my fingers are curling around the wire. The curling around the wire of my fingers shows that the blue magnetic field from the wire, the current in the wire, or electron flow in the wire, is like this. And so that's where you analyze on this side, they're in the same direction, and that's likes repel. And on this side, they're in the opposite direction, that's opposites attract. And so you've got a magnetic repulsion from the left and an attraction to the right combining to give you a magnetic force. So that's pretty straightforward to think our way through. It's just, you may have never thought of it. You know, like it's one of those like, oh, okay, that should make sense. But, oh, okay, I would maybe never have thought of it. There we go again here, likes repel, opposites attract. They combine to be a combination force. So the wire ends up the force sideways due to the magnetic force on each of the electrons that are trapped in the wire, right? If the electrons want to go to the right because of the magnetic force on them, then of course the wire ends up having to go to the right because they're trapped in there, right? So yeah. Does anybody want that page a little bit more?
Maybe just a minute more, please.
Yeah, fair enough. It's pretty fundamental, like describing why the hand rule, even like, why the force is the way it is, right? So it's worth a minute on there.
Okay, I got down when I knew.
Right on.
Thanks.
Yeah, problem. So so we've already talked about this, so I'm not going to show these videos right now, but we saw this previously, right? That's what causes the force sideways on electrons on the way to the front TV screen. It's what caused that beam of charges to go in a circular motion. If we were in class, I'd grab a big honking magnet and take out the black and white TV and even the color TV and show you. You can you have a TV screen. And you used to have like Prices Right on in the morning, stuff like that, but there isn't any open air signals, right? So now it's just going to be static in here, right? But it's just like static everywhere. So just like gray and, you know, specks everywhere. And then I bring a magnet near this thing. And so we have picture electrons coming out of the page. I'm going to draw actually just a dot with a circle for electron movement. Right, so electrons out of the page. And so electrons out of the page, I'm if I had a magnetic north, if I brought a magnet in that was strong, and the magnet had like a north pointing up, then picture electrons out of the page, north is up. These electrons are actually going to get a magnetic force on them this way, right? Just based on the hand rule for ease of analysis, instead of thinking about magnetic fields, we could, of course, do fields, because the fields would have been like this, right? Would have been like that around that electron that's flowing. And then we've got our good old likes repel business, right? So either way, you end up with a force sideways. But what that leads to is, instead of there being speckles in one spot, this, let's just say it results in, a big black section. So it usually looks like a big round or oval black section, where this is where electrons would normally land. And instead, they all land just to the right of it, and it's brighter, it's bright to the right of it and black where no electrons land, right? So you got that's what happens. You bring the magnet in and it moves them around. With a color TV, it's pretty cool, because the electrons they were just going randomly to all of the reds and greens and blues, right? So it was basically a white speckled screen. And then when you start sending them other places, they inadvertently land, on the red here and the green there and stuff like that. And so you end up with a bunch of colors, as you're just willy-nilly forcing the electrons to land in different pixels on different spots of the screen. So they actually end up seeing the colors. So it's neat. So again, if that's another one of those, like, please remind me to show that if we ever end up in room 124. There we go. So the main thing I want to talk about in this lesson, that was kind of, well, it's getting us started anyways, but we want to talk about electric motors. So you're going to, you've used tons of electric motors in your life so far. I want you to have an understanding of the principles that they work on. And so an electric motor has lots of little parts, and this is one that I would show if we were in 124 for sure. But the main parts here is you got these these I call it a split ring commutator, but it's a cylinder, and it has like a contact that gets split in the middle. So these two halves aren't touching each other, and it goes through essentially like a loop of wire. And then this dotted line in the middle is like the axis of rotation. So the actual picture of one, for example, like this is there's the axis of rotation, the bearings on either side. And then this is the commutator that has a whole bunch of different contacts. But ours is simple, where it's just one big contact on one side and one big contact on the other. And I'll talk about why there's a whole bunch of contacts with this one shortly. But these contacts here, the brushes, they call them, because they brush against this contact, voltage is applied to the brushes. And in effect, then the voltage is applied to the loop. And so you end up with electrons flowing through the loop. So picture electrons going in this wire right here. And we've got a north that is, so electrons that way, and the north is sideways from north to south. And so your palm of your hand, if your thumb's pointing in this direction and your fingers are extended to the south, is the palm of your hand facing up or down? You can see my arrow's already there anyway, so spoiler alert, but your palm should be facing up, right? Thumb into the page, fingers extended, curled out to the south, from north to south direction. There'd be a force up on that side of the wire, and then go around to the other side of the wire. You have to like twist your hand so your thumb can now point towards you. And the north to south is still actually towards the right, so your hand has to like flip and go from north to south to the right. And so now your palm's facing down. And so this loop of wire has a force up on it on one side and a force down on the other. So of course it spins. Okay, so it's going to spin up to this position like that, where it's like, and once it gets spinning, then it's going to have some angular momentum, it's called, but it's going to have some spin inertia basically, and it's going to spin around and then look just like this again. Once the brushes, you notice the brushes end up contacting the opposite side. Once it spins around, you end up with this situation happens over and over again. If it's horizontal like this, it gets a push up and a pull down, spinning it around so that you get to this position again. Push up, pull down, spins around, push up, pull down, spins around, push up, pull down, repeat forever, as long as you're putting voltage on there. That is the basics of how an electric motor works. pretty simple, actually, isn't it? You're thinking of it, you know, like we actually make these in class. I wish I had some pictures of them. I've made them in the past anyways. You know, just basically a wrap wire around a block of wood and then drill a hole through the wood and have it be able to spin. And, you know, like it's pretty easy to do. And I'll show you some videos of other things that are similar. Okay. So I have motors like this that are very, very easy to see that they're this exact design, and you see them spin when you put a battery on it. And we can understand why, and we can even predict which way it'll want to spin based on how I'm connecting the battery. So if I'm making, obviously, this be the negative terminal, then it's going to want to spin this way. If I put it backwards, it's going to want to go the other way. Any questions so far? Is how a motor actually works fundamentally as obvious as I'm thinking right now, having gone through it?
I guess a little bit, yeah. Still have to think about it, but
yeah, it's still a little bit weird, and like how would you make this thing and so on. Like I said, I wish I had pictures of the ones that I have made in the past so I could show you, because then you can see for yourself, like, oh, this isn't actually that hard. Let me just try and describe the ones we made, right? I actually have a block of wood, so I'll try and draw a block of wood. And the woodshop teacher at the time actually helped me out and made it. So he actually hollowed out these ends, right? So it was easy to wrap the wire, and you put a little wooden dowel between it. So it was actually a wooden dowel in between it like that. And then I made little plexiglass holders, basically. So a plexiglass holder from the side looked like this, right? And it just had a hole here and a hole here in order to be able to put these blue shafts through. So picture the blue shafts through there, and then your coil of wire is on there. So basically, one end of the wire here goes in and goes around and 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 around, and then out to here. Okay. So these two edges of the wire are acting as your split ring commutator. If I put a voltage onto here, you know, and onto there, then, you know, there's going to be electrons going through here. And if we had a north here, you know, we can analyze which way there'd be a force. Electrons going up, sort of, on my picture. The north is pointing to the left, so the force on this one with the hand rule would be down. Okay, so that's the physical construction to make a motor. You need two magnets, you need some wire, and that's it. And all I did here for the split ring, like how to get those together, is these wires. Let me redraw this actually. These wires, I just used the fact that copper is kind of springy, and just basically ran them against the thing. So I'll use a different color here. Let's use black for the source voltage. So we got a battery, and then basically the wire from there, I just have go through a bottom holes in here so that it holds them, and they just reach up and rub against the two here. So it's like it goes against like that and against like this. So it just brushes against those wires, and you can get this thing to spin round and round, no problem, by connecting a battery. So that's the basics of, you know, it's just a simple little motor. The next more complicated version of the motor, it's it's not super more complicated, but it's just a little bit of a different design, but we can easily analyze out what it would do. So I have this made a digital version actually of what I used to have as a overhead slide. So I had an overhead that looked just like this stuff, right? From like a, you know what I mean by overhead? I don't know if you do or not. It's like a light shines through a, you know, clear sheet and projects onto a wall, old school. But I had a pin thumbtack through this, and this piece was a separate piece and would spin. So we can analyze what happens. So right now nothing's happening, right? But as soon as I go like that, now I've got electrons coming in this side, hitting this commutator here, this contacting that metal, making electrons go down here, right? And then they go in behind, down in front, in behind, down in front, in behind, down in front, and so on. So I've got electrons that are going like this in the red here. Let's use red because it's similar to orange, right? So I've got electrons that are going down, down, down here, and then they're going this way. Got electron flow this way. Okay, so that's electrons going like that. So this hand rule here prompted you to think of this hand, like this design a motor prompted you to think of this hand rule, straight thumb and fingers in the direction and so on. This one is for the coil. We did do that before, right? Talking about curling our fingers in the direction of electron flow and the thumb points towards north. Yes, we have done that, right? I believe so. That electron flow makes a north this way. Okay, so by definition, there's going to be a south on the other end, right? What's going to happen to this armature that's free to go? Well, north and north is going to repel, isn't it? Right, so we've got a north and a north here. It's going to cause a repel, like a repulsion here. And we've got a south and a south here. It's going to repel as well. So this this coil of wire that's free to spin is going to repel, and it's going to go like that. It's going to go, whoa, it's going to get a little boost, a little push, right? And so even now, think of now, if the electrons are still contacting and so on, that means that this is a north still, and this is a south. So now it's even actually going to attract. So it gets another boost of a spin, right? So we've got the idea of the repelling here. So that's just showing that result. And then it gets around to this stage where now it's attracting, so it's going to spin even more. And eventually we get back to this position, right? It's here and it's spinning. And so it keeps spinning a little bit, and now it's contacting again. And so it's going to start over again. It's going to repel, and it's going to repel, and it's going to spin. So this long coil of wire functions like a motor as well. The analysis of how the forces are created, how the norths are created, and so on, is just a little bit easier to use the other hand rule, of course, because it's a different physical arrangement. Okay, so either one of these are nice, simple, basic motors, and they work. To get them going, you have to give them a little boost. Basically, you have to give them a little flick with the finger to get them spinning, and then they start going on their own. Actual motors look like this inside because you want them to be able to start on their own and reliably, and so they have a whole bunch of contacts, and that makes it likely that wherever the motor happened to stop last time it was spinning, it's going to be in contact with a coil of wire in here that is going to want to repel from a whole bunch of different norths and souths arranged around the thing. So essentially, this, not a good diagram of it, but essentially that's an actual motor. This is very basic motor, only has a single armature, single coil of wire, whereas motors are, the only way they're different is that they have multiple coils of wire, and that's what this is. They have multiple coils of wire all lined in the way they are, so they repel at each sort of, how many are there? Like how many degrees is there for each one? Like maybe 10 degrees? I don't know what there is there. How many armatures there are? Divide that into 360, and you've got the angle of rotation where you're going to have a push if voltage is applied. So that's an actual motor, like it's just slightly more complicated design, but not very. They don't do this as much anymore, but back in the day, not too long ago, in the 80s and the 90s even maybe, it was common for, like, if your alternator in your vehicle or your starter in your vehicle stopped working, you could actually, a common problem was the brushes were worn out. So picture the pieces of metal that are on a spring and they rub against this, right? They just wear out. So you can actually just take the alternator apart, change the brushes, and boom, your alternator is working again. So it was like a $5 fix back in the day when people used to fix things instead of just putting a new one in all the time. Previous ones have commutators you've learned and so on, right? They're like got this neat design, and I'm just going to show you some simple motors. This one's actually not much different. I put the first one does not have a commutator. It does not have a commutator results. Let me first. Wow, it has a commutator, but it's just a single-sided, right? It's really not much different than this first kind. Not much different than that, but I'll show you it. So that is a simple DC motor. Kingston. motor. Simple DC motor. There we go. It says no commutator. Maybe I'm wrong. Maybe it doesn't have a commutator. I think it does though. Let's see what it shows.
Hi, and welcome to today's tutorial on DC motors. This tutorial will be presented by Team A2 from Central Queensland University and will explain how briefly a DC motor works and how to build those up yourself. To make a simple DC motor,
Can you hear it all right at home? Yeah.
Yeah, I can hear it.
Perfect.
you will need the following equipment: a 9-volt battery, copper wire, a magnet, 2 paper clips, battery clip, and a piece of mounted cardboard. Other necessary equipment is scissors, glue, ruler, and tape. Tightly wind the copper wire to create a coil. Wind completely approximately 15
I should point out, he doesn't say it yet, but this is insulated wire. And so if you just had just copper wire and you're wrapping it around, the electrons aren't going to go round and round. They're just going to go through it side to side, right? So it has to be insulated wire, which is like wire that's painted with like an insulating varnish. So it's not just bare copper.
There's a free wire at both ends. These two free ends of the wire should be 180 degrees apart when the winding is complete. This is called the rotor. To secure the loop shape permanently, wrap each free end through the loop and around the coil with the wire 2 to 3 times. Make sure the binding loops are 180 degrees apart and wrap tightly around the coil wires. Check the balance of the coil aperture by spinning the coil by the axis between your thumb and index fingers. Sample the top half of the insulating end. Do the same to the other free end. Make sure the shiny bare copper side faces up on both ends.
So this is even less effective because it only has one contact per turn rather than 2 contacts per turn. But that's essentially a commutator. It's just a one-sided commutator. So he's just he sanded the varnish off on the top side only, right? And so basically, it's only going to have current flow when it's oriented with that side touching the wires it's going to balance on. And so that's when it gets a little push. And then it spins around and gets to that position again and gets a little push. So when we analyze this one, we're going to be talking about the left-hand rule where you coil your fingers in the direction of electron flows. It's going to be easiest to analyze because we've got a coil.
Clips into hooks as shown.
So you need 2 little hooks for it to rest in.
Cardboard block. Place the coil onto the hooks in the paper clip post.
So if you have insulated wire, you can actually make a little motor. So there's the magnet to be able to cause repulsion.
To start the DC motor, give the coil aperture a slight spin.
And there you go.
Disconnect the battery from the clip to turn.
You got a super basic little motor.
Michael Faraday in 1851.
Kind of neat, right? So picture electrons flowing through, and you're like, oh, so that's going to make a north facing down. Let's say maybe if that happens to be the north, then it's going to want to repel. And so you give it a little spin, and it basically, while it's going up, it stops actually making a north. And so nothing's repelling it from going back to here. So it gets a little push away, and then just freely wheels, and then gets a little push away, and then freely wheels, and gets a little push away, and it just keeps going. So that is a very easy to understand little electric motor. The Russian guy, but he's funnier. He is kind of funny. Where is that? Here, the Russian guy. He's hilarious. I don't know if you've seen the crazy Russian hacker, they call him. You should YouTube him if you haven't seen him yet.
What's up, everybody? Welcome back to my laboratory. Safety is #1 priority. And today, I got some new magnets. That's the strongest magnets in the world. And I got like 10 of them, and we just need one piece. This is like a super magnet, so you can really break them apart that easily, you know, they're really strong. And today, I'm going to show you
how to make motor.
Using just battery, screw, small piece of wire, and electric tape. A little bit of electric tape, and of course, no magnet.
Oh, this is the other kind of wire. This is the other kind of motor. Actually, I forgot. This is so the actually, I'm not sure. Let me just see if this is the same one. You might have a coiled wire version of it. He's got ads.
You load your 4x4
He's making money.
2x4s? We built a new program for pros, VIP Pro.
This might be the same one. I'm not sure. But he might have a coil wire version as well.
What's up, everybody? Welcome back to my inches and spin around it. You want your wire to be pretty long so you can spin it many times, you know?
He's doing the same thing though.
Alright.
So I should probably
You
go to
want
the
to
next one.
grab
But
your knife and take the isolations off. Do not cut yourself.
he's doing both sides, which is
your
strange.
isolation off on one side, do it on the other side. Then you want to get your paper.
So same thing, but again, like he's funny. But we'll see him on the other one anyways. So let's talk about the other one first or next here. So the one I'm already partially going through here. So it seems like that's already the one, but this is the kind of motor he's going to be making here with a screw and a battery and so on. So I think I can just let that play.
First thing we're gonna do is get our body. I have a AA body that will work, and grab our wire and put it on top of it and tape it with electric tape.
Or just hold it with your finger.
So it will not burn your finger.
So this is one you probably can make at home if you have any of those little magnets.
Don't matter, like that.
Just a little disc
You
magnet.
see, we have the body and a wire coming out like that. Then grab a screw and put the neodymium magnet on the bottom. Bounce it so it's like in the middle. You see what I'm saying? Then you're gonna put the screwdriver on top of.
So I made a little note here. Of course, it'd be easier if you used the other end of the battery, because the other end of the battery is a big flat circle rather than that little trying to get to go in that little bump. So you're gonna see it's gonna fall off that little bump once in a while. But here we go.
Like that on that thing like that. And then grab a wire and touch the magnet.
And
Guess
so,
what happens?
hopefully you can see there that this screw and magnet is spinning
smoke.
like crazy.
Pretty cool, huh?
It
Very
spins like
simple
crazy
model.
just by
Let's check
rubbing
it
the
out.
wire against it. See it there? And so that was a bit of a viral video back when this was first sort of shown. So the most simple mode in the world is the one we're basically watching right now. I don't know if it's the exact one or not. Yeah, it would be that one, I guess. The one we loaded. And then the other one is called, let me just make sure, homopolar motors. It's just a more scientific or less humorous version of this. So let me just go homopolar motor. Actually, that can be too many options here. Homopolar motors here. So this one's, I think, easy to follow as well. So there's the motor working. So you get a battery, stick some magnets to it. Ooh, this is a different version. Sorry, I don't know if I want to show this one right now. Neat though. So you can analyze how that one works. The main one I wanted to show. All weird versions of motors. This is the one here that I kind of want to talk about first anyways. So anyways, how does it work, right? So he, in this video at some point, he actually says, geez, I wonder how much, in the Russian accent, Kayla's good at it, I wonder how much energy it's producing. And of course, I'm commenting here, it's like, it's not producing any energy, it's consuming energy. I think he meant like how powerful it is, I think is what he was saying, right? But so the task is like, to sort of think of like how this thing works, right? So this simple homopolar motor here, how it works. And what you want to do to figure that out is you want to think about where electrons are flowing and what direction a magnetic field would be in and what magnetic force there would end up being on those electrons, right? And, you know, clearly there must be a force like sideways like this and opposite side on the other side, you know, that's making this thing spin, right? And so we want to end up analyzing that there's a force on those electrons. So yeah, depending on what side's which on this battery here, I never remember. But if electrons are going like down and in through here, then we have electrons that are going in to the magnet. I'm going to use green. So we got maybe have electrons going this way. Like I said, I forget which side's the negative on a battery Duracell. But if we had electrons, that's electrons going into the magnet, right? And then it's pretty simple analysis here, where you're like, if the electrons are going into the magnet, and the north is, say, straight up or straight down. Let's go straight down, right? So electrons are going into the magnet. If the magnetic field is straight down, the push on the wire is in the direction of that blue arrow. And then on the other side, the electrons, well, it's just, actually, that's the only spot where electrons are moving. We don't even have to have this other arrow because we don't have electrons moving over there. So I should get rid of that other arrow. Hoping you're following me at this point, where you've got your thumb pointing in the direction of this tiny little green arrow here, electrons going into the magnet itself, like current flowing through that metal magnet. And then those electrons moving inside of that magnet have a force to the kind of to the right, I guess, in this picture, because of the magnetic field that would be down on this disk magnet. And that's what this picture shows over here too. The idea of electrons going, you know, whichever way they're going, and then the magnetic field's up and down, and you end up with a force sort of sideways on that. And so this is how you do it, right? Connect a wire, you know, and have it just, the wire just brushes against the magnet, and that's what's causing the force. So they're showing current flowing this way, magnetic field up, and then the force into the page, because the I is current flow positive, so it's with your right hand. So right hand thumb pointing left, fingers pointing up. The push is towards the screen. So it's a very, very explainable, simple little motor that works. And this is what we were analyzing over Christmas holidays with my brother-in-law. And he was like, I was talking about electron flow, and he was all worried. He was like, wait, we can't talk about electron flow. We have to talk about flow of positives. I'm like, okay, I can use my right hand if you want. You know, it's the only difference. The homopolar roller, just neat little applications of this that are totally analyzable. I'm not going to spend time analyzing all of them, but neat to see. Homopolar, homopolar roller. Which one's slow? That one says slow, probably meaning it's like painful to watch. So the homopolar roller looks like this. Eventually here, you can just roll across the table because of the battery connected to it and so on. So the little loop of wire, and so picture, you know, the loop of wire there, and so you're going to have electrons going. I'm going to use my mouse here. Maybe electrons going up, right, through the material to the conductor. So those electrons going up, and if you had a magnetic field that was electrons going maybe to the left, and then the magnetic field up or down, you get a push forward, right? So you end up with a push in that material because of the electrons flowing to this wire. So you just have to analyze whether you're thinking of electrons going left or up or whatever, and depending on which way the magnetic field is too. But certainly it's not too hard to analyze that and sort of get the idea of it. So that's the mechanism there. You got a battery connected between two circular disc magnets, just a piece of stiff copper wire bent so that it sort of hangs and rubs over the top of the two magnets, and it'll just go rolling across the table for you. It's a motor that's moves on its own. Anyways, so this lesson, all I've been talking about along the way here is just kind of describing and being able to predict what happens, you know, how this turning off magnet works, how fridge magnets work, how motors work. There isn't any you know, mathematical equation questions to do with this. Okay, these are just all applications of the previous hand rules that we already talked about. Any questions? All right. So to make up for the lack of equations and questions you can do on that lesson, here's Ampere's law and the force between two parallel current carrying conductors. And it's actually a pretty significant historical development here because it led to the definition of what an ampere is. This one where you got two parallel wires carrying electricity. So just remind ourselves here, Ørsted accidentally found that electrons flowing causes magnetic fields, right? So he accidentally found that. So he observed, of course, that more current leads to more force. The farther away you are, apparently just to do with distance itself rather than distance squared, reduces the force. And so basically we're saying the magnetic field strength around a current carrying conductor is proportional to I over R. And so what that leaves us with is a Ki over R, and of course K is just your proportionality constant. Okay, so let me leave that with you for a little bit just to get the idea across that we're trying to talk about the magnetic field caused by the current in the wire. So this is magnetic force, and therefore the field, of course, right, caused by, that's force per charge once you're talking about strength and so on. But anyways, this is caused by caused by the current in the wire itself. So we're not talking about the magnetic force that results from another magnetic field and so on. We're just talking about like the force that would be on a magnetic object nearby the wire. You know what? I'm just realizing here. I shouldn't be saying force at all. I should be saying B the whole time. Oof. That was a edit error. Magnetic field strength, just B itself. Tesla and so on, right? Sorry about that. B. So this is what I was saying. Magnetic field created by current. Wire. So we're talking about the B. The magnetic field actually created anyway, so yeah, we end up with B equals K over I. I have to make a note to fix that in the copy of this lesson. No, it's got to be a B. All right, so he found that out, right? This relationship. So Ørsted found this out. He did this and was like, oh, this is pretty cool. I have a relationship. Remember, this is the one where there was a video and there was a piece of that wooden apparatus where he could move the compass closer or farther away and from the wire, and he could put different amounts of current in the wire and so on, right? So that was good. That was pretty good, right? Ampere. So that's Andre Marie Ampere from 1775 to 1836 is the Ampere person you think of when you think of amps and current. So he heard about this and thought, it's pretty cool. I want to develop a general relationship between any current carrying conductor, not just straight wires. That's what he wanted to do, and the strength of the magnetic field it produces. And he was successful, and the result is called Ampere's law. Okay. Just trying to decide whether we put a box around that one. I don't think we do. You could, but it's not really one necessarily that you're going to use as much because we're not even saying what the K value is, right? So basically, this is there was a proportionality constant between them, but really the B wasn't known, right? Wasn't a number at that point, anyways, and so the K value was not really a number either, and so we're not really thinking of that one as an equation we're going to use a whole lot. We're going to wait for Ampere to really nail it down for us number-wise. Okay, so Ampere's law sounds more complicated. It sounds complicated, but let's just go through it. Okay, so Ampere reasoned out and thought, had a good idea that along any closed path through a magnetic field, so a closed path, this green path on this one, the sum of the products, so add up all of the products of the magnetic field that's parallel to the path segment with the length of the segment. So basically what you're going to do is you're going to multiply the magnetic field times the length in a whole bunch of little chunks and add them all up. Okay. The result of that is essentially the idea of like how strong the magnetic field is, right? He said that the result of that is going to be directly proportional to the current that's passing through that area. And so in this case, you have a wire that's straight up in the page here. And so that's the current that's flowing. And he's saying, like, if you take the magnetic field and multiply it by little sections of length all the way around, then that value you get when you add up all those pieces will be proportional to the actual current. Okay. And so what we've got here is this, I'll just show the pieces here. B with a parallel sign is obviously the component of the magnetic field parallel to the path, right? And when we say the path, we're going to talk about a whole bunch of little delta L's of the path. We're going to talk about a whole bunch of little sections of the path. And so you'd have a little section here and a little section there and a little section, like all the way along. So like a tiny little delta L section. And then basically in that delta L section there's going to be, obviously a magnetic field, and the component of it in the direction of L we're talking about as a product right here. Okay, so I'll just erase that because I don't want to have that too ugly there. But we're talking about the magnetic field times the actual like section of length. The E symbol, you may have seen it in the past. Sometimes you see it in like spreadsheets. Actually, you use E to mean add up all the stuff. It's actually a mathematical symbol that means the sum of all that stuff. Okay. In calculus, once you see calculus, you'll actually have sum of like n equals a to b. So you're like actually saying where you're adding up from one spot to another. Okay, so that's how you start out in calculus, is the idea of adding up all of the products along a set of numbers or a defined space, in this case, like all the way around.
Mr.
Yep, go ahead.
What's the two dashes beside the B for?
That just means parallel. So that's the notation for saying we're talking about the component of the magnetic field parallel to the path.
Okay.
Okay, and that's all that's meaning. Yeah, so it's magnetic field, but it's specifically magnetic field parallel to the path that you're talking about. In this case, we're talking about a path that goes all the way around a current carrying conductor. Okay, so in this case, it's easy because it's a circle, right? So we're going to be able to use that math to help us get an answer. So back here, we talked about how Ørsted found this out and reasoned out that we've got a proportionality situation. So there's a proportionality constant, but he wasn't able to get I don't know. I want to say he sort of got a number, but it wasn't really quite the same, right? As what we're doing here. So mu naught is the proportionality constant that Ampere found. Okay, and so how strong the magnetic field is kind of determined by how easily a magnetic field goes out into space, right? So they actually call it the permeability of free space, which is such a strange name, but if you think of it in the terms the way I just described it, it should help you understand why they call it that. So mu naught is, instead of K, right, it's the proportionality constant, okay? So we could have said, I guess we could have said the sum of all of the magnetic field portions that are parallel to all these little guys is proportional to I, right? So we could have said it like that. And then we could have rearranged things here. We could have said, okay, yeah, it's proportional to I. And then, so of course, the idea is that it's equal to, the product is if you have like a proportionality constant. So I'm just going to put quotes with a K there, saying like, that's a proportionality constant. We typically see those as Ks. Well, this time finally we didn't actually, which is maybe good. That value for that permeability of free space worked out, because of other choices that are going to be made shortly, to be 4 pi times 10 to the negative 7 Tesla meters per ampere. So don't worry about the units, just use the number 4 pi times 10 to the negative 7. This general relationship, this general thing that's true can be used to determine the magnetic field for the strength, can determine the magnetic field strength, the B value, right, around any kind of current carrying situation, not just straight conductors. So one small note about this 4 pi times 10 to the negative 7. Please, if you have a calculator nearby, please try this out or try it out later if you don't have one nearby. But if you hit 4 and then your e to the whatever, you know, like your 10 to the whatever. So if I hit 4 and then I hit e to the 7 and make it a negative, I'm going to have a number 0.00004, right? If I hit 3.14 and hit e to the 7 negative, I've got a 0.000000314, right? So you can see my calculator is working in logical ways. The issue for this one that I discovered with my calculator, at least, is if I say 4 times 3.14, I get an answer of 12.56. Okay. On my calculator, with my 12.56 in the calculator there, if I now hit e to the 7 negative, it doesn't keep that 12.56. I'm actually just doing times 10 to the negative 7 without the 12.6. So the 4 times the 3.14 is 12.56. I have to actually clear the memory, hit 12.56 with my calculator, like punch it in, then hit e to the 7 negative, and I actually have now the 0.0001256 number. So what I'm cautioning you with is when you're doing calculations with 4 pi times 10 to the negative 7, you have to make sure your calculator does 10 to the negative 7 of the 4 pi number, rather than thinking of the times 10 to the negative 7 as like a new thing, right? Because if your calculator has a result in memory, and then you say, 6 plus 2 is going to give you 8, regardless of what you had in memory, that's what's going on. Okay, so you have to make sure it's like, I want to have that thing to the power of whatever, not something new. So just watch how the calculator works there. Make sure you're actually getting the 0.0012, whatever the number was, 56. So in order to see that this weird relationship that Ampere talked about actually works, we're going to see that it's going to give us the same result as Ampere reasoned out. Not Ampere, sorry, Oersted, right? Oersted reasoned this guy out here, B equals Ki over R, right? So we're going to see that Ampere's law gives us that relationship, okay? So we're going to take that circular path, and we're going to say, okay, well, along this path, we know that the magnetic field's actually a circular thing. It's got a north facing all the way along, right? Using your left-hand rule, or a right-hand rule, I guess in this one, you get your I, your positive flow up, and your fingers are curling around in a counterclockwise direction. So along the way here, your B values at any spot are just like, radially, not radially, going along tangentially, I guess is the correct word for that, but going along that circle pointing to the side. Okay, so what we know already is that the magnetic field parallel to the path is always just the magnetic field itself, so we know it's a constant value. And that's a known thing already. It's already been discovered, basically, right? So what we're trying to do is we're just trying to get an equation, quantifies it, puts numbers to it. So Ampere's relationship, we got the sum of all the parallel bits and multiplied out, right? So that it's always just B instead of parallel components. We don't have to do anything to the magnetic field conveniently for this development. The next step is to say, well, okay, what's the sum of all of the delta L's? What's the sum of all of the delta L's? So to go along with this parallel bit here, there is a delta L, right? There's a section of length. There's a delta L. So if you add up all of the sections of length for this whole shape, I'm going to say shape so I don't give away too much here. If I add up all those sections of delta L's, what do we end up with? Right? The sum of all the delta L's. We're making a circle. So basically I'm asking you, how long is it around a circle? And that is a known thing, right? We're talking about circumference, right? And so you can actually put in there, circumference is 2 pi r. So we're already talking about r, the distance away from the wire. super convenient numbers, isn't it? Okay, so basically we know this is going to add up to b 2 pi r, right? So remember, the formula is, I should grab the original Ampere's law, maybe this guy, put it above that. So remember, we're talking about, you know, the sum of parallel bits, blah, blah, blah. We're saying it equals mu naught I, right? And so you're like, oh, okay, so b 2 pi r equals mu naught I. And so that allows us to just solve for b, right? So you get b equals mu naught I over 2 pi r. So this portion, it's going to say in these little squares here that I'm going to reveal in a second, but this is the k value that Ørsted would have been referring to. K value that Ørsted, O-E-R-S-T-E-D, I think it was, found. So basically, you know, the actual k value that was the proportionality constant when Ørsted looked through it in the more simplistic way, right? Saying, oh, it's proportional to this and whatever, right? Reasoned it out. That k value, Ampere found sort of a more fundamental value to do with it, that it's mu naught over 2 pi. Okay. So that turns out to be the same proportionality constant Ørsted determined. And remember, mu naught is equal to, let me just gather that here. It's just a weird number. Well, that's the value that we know mu naught is from having actually calibrated it based on choosing what a current was. But anyway, so mu naught is 4 pi times 10 to the negative 7. So that is a new equation for us. So let's load up that equation sheet. Do I have it ready to go here? No. Course files. Equations. And so our next formula is magnetic field around a current carrying conductor. Actual magnetic field, all right. Come on. All right, so that's the one that I almost sort of revealed yesterday by accident, but it's magnetic field produced by a current carrying conductor is B equals mu naught I over 2 pi r. So you're going to put that in there. You're going to put that, you know, mu naught equals, or I'm not sure if you're making a formula sheet like this as you go along. You probably should be, but obviously I'm continuing to fill in this equation sheet as we go. This is the note about being careful here. 4 pi e negative 7, right? I have to do 4 and then maybe e negative 7 and then multiply by pi to make it happen naturally. Because it won't take the result from 4 pi and use it. So that is Ampere's law. Okay, so you can see that it was able to, this is equivalent, right? This is equal to B equals K I over R that we had from the previous one, right? It's just that now we're being more specific about what the K value is. So you're going to use the 2 pi, you know, mu naught over 2 pi R business. Do I need more time on this page?
Just a minute more, please. Sorry.
No problem. I still feel like I'm talking to you specifically whenever I say this, but I'm going to say, maybe I'll say, do we need more time on this slide? Everybody in the class, how come he's so concerned about whether a page is ready or not? What about us?
Well, I don't know about other people, but I am done.
Good enough. Everybody else will cue their mic if they need more time as well, I'm sure. All right, so a couple of neat applications of Ampere's law. Coax cables, right? The kind of coax cable that leads to, like, from a satellite dish to a TV to this day, actually. I don't have as many of these in my house anymore that are functional because I have fiber optic now. Woo! That's how my internet's good. Someday, Paige. That was actually for Paige. So there we know what we can apply Ampere's law around a coax cable. And long story short from this paragraph here is because we've got current going this way and current going that way, the net current is 0, right? So where are we going here? The net current is 0, which means the net magnetic field is 0 because of because it's proportional to the the sum of all of the blah blah blah. Sounds like there's a tick in my house. 1 sec. Your best to kill it. Best to put it in. Flush it. All right, the tick has been flushed. You either got to flush it, burn it, or crush it with a hammer against concrete, because stamping on it with your boot doesn't kill it. I've tried. Okay, so we know that. Let me just go back to this, and we're saying like it's proportional to the current, right? So is that what we said back here? Proportional to current. Yep. Good. Double check and make sure everything's consistent. But yeah, so that's why coax cables are done the way they are. So this metal wrap around here is the return current, and so it shields the signal from magnetic fields outside of it. Plus, it also shields anything, like it stops the magnetic field from creating a magnetic field as well. That's the design of a coax cable. And another application of this, if we're ready for it, probably because that was pretty simple, right? It's proportional to I, and there's no net I, so no field. This one's a little weirder, so we'll make sure to do a good job here. But this is about getting the value for the magnetic field inside of a solenoid, inside of a coil of wire. And so that's going to be one of our. I have that thing twice. Eh? Yeah, I guess I'll have to rejig my table here because I don't need that one, obviously. So I guess I can just do this here. Magnetic field around a coiled conductor. So we are going to end up having a result of for a magnetic field around a coiled conductor using Ampere's law. All right. Ampere's law is intimidating, but I'm going to walk you through it. Okay. So we've got this coil of wire, and they're actually showing like current flowing out of the page and going around, in a coil of wire to here, right? So you've got this coil of wire that's like going like kind of whatever, like this. It's hard to visualize. So I'm going to erase that, but I just wanted to help you visualize it. So we've got the out of the page and then into the page going around and around, right? We're using Ampere's law and choosing a closed path, right? That it has the area we're looking for in it. So a closed path here. And so we got this rectangle X, W, X, Y, Z. And we're going to analyze out Ampere's law along different paths. So the first one, the red ones that I've highlighted to make it easier to follow, right? So the WX and the YZ, the red ones. Those ones, the path is perpendicular to the magnetic field, because we know the magnetic field due to so we know the magnetic, I have to get this right in the head. The magnetic field is the red here, right? Just to remind ourselves here, the red is the magnetic field. I was stumbled up myself trying to think about the magnetic field around the wire, but that's not what we're talking about. We're talking about the magnetic field here, right? That's B. So look at, it's at 90 degrees, obvious as anything, right? So we got 90 degrees there and 90 degrees here. And so these are 0. So in our sum of all of the, products of the magnetic field parallel to the little sections, all along the red sections at the end, there's no contribution to overall magnetic field strength. Okay. Along the WZ, well, that's going to be 0 as well, from a previous definition that the magnetic field outside of a field has been, it's just known to be 0, right? So there's nothing along the green one as well. We're not trying to prove that right now. We are just trying to find a number for the strength of the magnetic field, right? So basically, we know the magnetic field is, sideways. This is the left-hand rule. Coil your fingers and your thumb points in the direction of the magnetic field. We know all that already. We're trying to figure out the value of it, the number, okay? So this is maybe mislabeled up here, where it's determining the size. My keyboard's not determining the number value. Not really explaining, it's determining the number value, right? For the magnetic field from a coil of wire. So that's what we're really doing. So another correction to make. We're determining not whatever. So it's page 6 on 24. Just like corrections to make and editing this as I go through it. So we got 0 outside. And so really we're just left with magnetic fields along that line inside that's parallel. So now we're talking about path XY, which is the middle section here. I maybe could put a blue line on there and have that color coded as well, so easy to follow. And so we're talking about path XY, the blue one, right? That one, there is actually a value. And so we can say, oh, okay, so we've got magnetic fields along there. So that's the only section that's contributing. So that means that the sum of, I've highlighted it in blue here, the sum of that, that's convenient because I used blue here just now. Cool, that worked out. The sum of all of the little sections, delta L, add up to L, capital L, like the actual length of the coil. So let's add that in. So capital L equals length of coil. Not the length of the wire wrapped up in the coil, it's just the length of the coil itself. That'd be blue to match the diagram. So we add that, we actually get L. The B value is just the B value because the B is parallel to the length of the coil, right? So this is just B right here. That's just B because B is parallel to L. So we're saying, okay, BL is whatever, right? So now this part here, mu naught is obviously there, right? The N times I is because in this diagram, clearly we've got currents and we've got however many wraps of the coil there is, right? That's how many currents there are. So this N is just the number of turns in the coil. Each turn of the coil, coil turn, leads to whatever, right? Leads to current in the region. So thanks to Ampere's law, we can solve for the magnetic field and say, oh, the magnetic field around or in magnetic field in the middle, right, in the core of a solenoid or a coil of wire, is mu naught Ni over L. Okay. And that's how it works. And I get that Ampere's law is intimidating, but having worked through it so nicely for these two examples to get a number value here, first of all, confirmed, right? We're confirming the known formula. And then now we're actually developing a new formula that we didn't really have a number for. But would it be easy to sort of reason this one out? We're like, oh, well, magnetic field is going to be proportional to the number of turns. Of course, more turns means stronger. B is going to be proportional to I. Yeah, that makes sense too. And if we had a longer, if we stretched this thing out, like if the turns were like super compact, right, that'd be more dense. Versus if the turns were spread out over a long distance, you can picture how that's going to make it weaker. It's going to spread out the field, right? So they'd say like B is spread out. And so you can picture how it would be inversely proportional, right? So 1 over L, longer L, less B. And so our logic actually can lead to this equation as well from that one. Okay, so and it would be proportional. So there's your proportionality constant business. And we're actually going to calibrate that. I should add up here that I mentioned earlier. This we're saying back here that that mu naught is 4 pi business, right? Mu naught is 4 pi, but this hasn't really been, in our slides at least, hasn't been justified yet. So this number is coming soon. Number choice coming soon. The number was calibrated based on a situation that's kind of more complicated to analyze. And so it's common for people to teach this first and then later on say, oh, by the way, this is how we actually chose that mu naught number. Okay, so we're about to do that as well. But before we get there, this is a type 1 question, if you want to call it that, right? Where it's like, hey, I know a formula. I can plug numbers into it. I can solve. So that looks like this. They gave us L, they gave us N, they gave us I, they're asking for B. You just have to recognize that it's a core of a solenoid magnetic field, right? In the core of a solenoid, you have to go to the equation sheet, pick the equation, which is going to be this one, right? The one we just wrote out. I am not even suggesting, I'm not even like, it's not even like you don't have to memorize this formula. I'm actually suggesting you don't memorize it. Like, except for maybe the idea that it makes sense, it's proportional and whatnot, but I don't want you to stress out about having to memorize all these equations. I want you to just use your equation sheet and use it. It's kind of like grade 10, 9, and 10 science. I don't encourage you to memorize the periodic table. Like, what's the point of that? The periodic table is there as a tool to use to help you solve chemistry questions, right? These equations are tools to use to help you get answers to do with physics questions. So please think of it that way. But yeah, numbers are going to fire into that, and you're going to calculate out the magnetic field strength. Okay. View full screen, entire page, whatever. And boom, there we go. Entire slide. View entire slide. Okay. That's a basic enough one. I don't want to stay there very long. But this is the weirder situation that actually leads to the mu naught number. So we're looking at the magnetic force that results between two current carrying conductors. And our previous analysis about magnetic fields individually can help us figure this out. Okay, so if we have a magnetic field like this because of electron flow using your left-hand rule, and then like this because of electron flow using your left-hand rule, then you can see in the middle, we've got magnetic fields down the side, magnetic fields that are up. Those are opposites, right? In the two-dimensional drawing, it looks like this, but they're opposites, and so they're going to attract. And so if we have electron flow in the same direction, this is worth, it's not emphasized quite enough on this page. So I want to just sort of point out if they're in the same direction, I want to just write it like this instead. Right? Or even like, there we go, that's even better, right? So if they're in the same direction, right? That's what we're talking about here. I'll just maybe, so if they're in the same direction, then notice that we end up with attraction. So that leads to attraction. Sorry for yelling. Sorry for yelling in a text message. So that's that. And then opposite direction stuff, you'd actually end up with them in the same direction. And so now I'm going to say opposite direction. And that's going to lead to repulsion. Or just repel, because I don't have enough room. Okay, so same kind of stuff. So turns out analyzing the fields leads to these results. Okay, so it was just kind of discovered, right, that current through these wires side by side leads to attractions and repulsion. Okay, this again is what leads to the number value for the mu naught Okay, so this leads to the number value or the number value mu naught. Let's just say mu naught, mu 0. That's what it's called, the mu naught. So number value mu. One more here. One more try. Mu naught. Need to not have the eraser always grabbed here. 4 pi times 10 to the negative 7. Okay, that's what leads to that number value. And the reason that how that works is basically what they did is they decided on the size of an ampere. And I'll get to that in this slide here, but they decided on the size of the ampere. And of course, ampere's involved in this, and that's what, like that's based on who did it, right? So Ampere decided on the size of the ampere using this apparatus. So I'll get to that. Do we need more time on this page though? This slide? Hard habit to break. Nobody says. All right. So obviously 2 current carrying conductors, we can analyze this out pretty easily. We're like, what happens if, right? So if we've got, what are the things that are going to change? If we had more current, then obviously we're going to have more magnetic force, right? We're going to have more force. I probably should just say the B, but I'm not going to change it yet. So if you had more current in either of them, you're going to have more magnetic field or more forces resulting. If there's a longer section, right? If you have more wire that we're talking about, then there's going to be more force overall. So L, that's different than the solenoid, of course, because the solenoid spreads the coils out. This is just like, the more wire you have beside one another, the more force there's going to be, because all the forces all the way along are adding up. If you're further apart, of course, it's going to be less force. Turns out to be directly proportional. That's weird, right? That it's directly proportional instead of the square business. There's probably a logical thought to do with that, but let's just go with it. But that leads to this, that the magnetic force between them, it is just force in this case. The magnetic force between them, good thing I didn't change it, it's just the force between the wires, right? We're saying it's proportional to IL over D. So that means that we have a KIIL over D, right? The proportionality constant that we would just basically sometimes have the luxury of just measuring because everything else was already decided. In this case, the current values weren't really decided yet, and so we're able to calibrate it. What do we have here? Like how we've calibrated things in the past, where it's like 1 Newton makes 1 kilogram go 1 meter per second squared, right? So often we choose K values equal to 1. And this is an example with mass. 1 Newton makes 1 kilogram go 1 meter per second squared. Another example is, so this is usually K is equal to 1. 1 ohm, 1 volt, and 1 amp go hand in hand, right? So what happened in this case is Ampere chose a value of 2 times 10 to the negative 7 for that number, 2 times 10 to the negative 7. And the reason that was done was so that if he had chosen K equals 1 like normal, then the amount of current flowing through a circuit in your house would be 0.000000015 amps. And he kind of felt like people aren't going to want to work with like microcoulombs and microamperes and milliamperes all the time. So he chose a proportionality constant value pretty much at random. He's like, oh, let's use 2 times 10 to the negative 7. I have no idea why. Okay, but he did choose that, and then that number is the one. So this is him saying here, like he basically said, okay, well, 1 meter of wire with 1 meter of wire produces a force of 2.0 times 10 to the negative 7 newtons when there's 1 amp flowing, right? So if 1 amp is flowing, then it makes this much force. And if he had have chosen a different number here, then that would have been a very different ampere number, of course, right? Is the idea I'm trying to get across. So the result was Where am I going here? Let's just go to the equation sheet. So the equation sheet, do I have it here? Force between two parallel conductors. So remember I said the K value, the 2 times 10 to the negative, whatever that was chosen, that's really this, right? That's the K value. So it's written as, I didn't do that on the other slide yet, but it's written as mu naught over 2 pi for the same reasons as Ampere's law analysis from before. So this one can be written in more than one way. If you're adding to your formula sheet, go ahead and add that in. Oh, and this one's already there too, of course. Didn't show it yet. That's just the K value, of course, right? That proportion, I'm going to put it in quotes because it's like not really referred to as K typically, but proportionality constant, always shown as K's typically. So this equation is sometimes you prefer to think of it as force per length, but this is just the direct version of it where it's like plug in the numbers, boom, get the force between the wires. So this is another example of a new equation, plug in the numbers. So you're going to say, ooh, 2 parallel conductors, I want to know the magnitude of the force. I'm going to go to the equation sheet and I'm going to pick out this one. And I'm going to plug numbers in, get a value. And I know we're dying in time here, so I have to just sort of jump to the next one because I want to show you that they can sometimes just ask for the force. Sometimes they ask for the force per length. Okay? The equation sometimes is manipulated to force per length. And so if they had have asked in the previous question, what's the force per length, then we would have just had the numbers plugged in without the length, right? And it would have been this many newtons per meter, which for 2 meters ends up being this value. Right, see how that one's double, of course, right? Because the force per meter, and you got that much per meter, and you got 2 meters, so it's double the value. So just if they're saying force per length, it might be easier to grab that one, but really no, or just no, right? So or solve, right? Or solve and get that one from the original equation. So you could just take the normal equation, this one, and just solve to get force divided by length. It's common for people to ask that instead, right? So take your regular one and just solve for that. You don't have to think of it as 2 separate equations if you don't want to. And ding, the bell went. Still half-hour class left technically, but those are questions. So these are going to be use the equation, plug in the numbers, get an answer. I think exclusively, if I remember right. We did it. Any questions?
So you said that you were going to send that assignment thing. When would it be like due?
I would think that we could just say like, it's due a day or 2 later each time. Would that make sense?
Okay.
Yeah. I think it's going to be reviewed.
One today. When would that? Because like it's the weekend, so when would that be?
Yeah, like let's say, so if I send one out today, probably will be. I just have to get to it, do it. But anyway, so if I send something out today, then is it due like maybe for the weekend situation, we can say at the end of Monday, so you have a chance to ask for help without necessarily feeling like you're bothering someone on a weekend. But I am okay with you emailing me the weekend. It's just I may not get to it if I'm out in the bush in the Jeep or something, of course, right? So
okay, thanks.
So let's say end of Monday for the one that's going to come out. Yep.
All right.
All right. Okie dokie. So that is it. So lots of ideas today, but not much new quantitative stuff. So there you go.